Hi all, welcome back to Math 521 movies. Uh, Today I'll have a short discussion of the Notes 18 on nonlinear problems. Um, in the context of finite element and finite difference and spectral methods approximating nonlinear differential equations. There's a discretization, so you end up with a finite number of unknowns, which you can think of as in a vector capital U. And the approximation of those problems, steady state or implicit time stepping, always results in a problem that looks like this. It's a nonlinear system of equations for the unknown vector u. So this is if u has n components, then this nonlinear system has n nonlinear equations. And there are various approaches to approximating solutions of those nonlinear equations. The method which is, the fastest convergent is called Newton's method, which you may be familiar with. In the scalar case, it's usually taught in a first year calculus class. In my experience, many students, even at your level, have never seen the vector version of Newton's method, which shocks me. But I have some basic notes on Newton's method and a couple of other iterative methods from the class I taught last term, which I've posted. So you can see Newton's method, remind you what that does in the scalar case, and then also remind you or see for the first time how this works in the vector case. Basically, what you have to do is you iterate to find the solution of the nonlinear problem, and at every iteration, you have to solve a linear system of equations, and the linear system of equations is the nonlinear system linearized around the current iteration that you have. And when I say linearized, that means you need the partial derivatives. You need the partial derivatives of every equation with every unknown. That gives you a matrix of partial derivatives that's known as the Jacobian matrix. And again, the first part of the notes that are posted will take you through all of this if you've never seen it before. And as extra perspective from what we've been looking at just recently, you can think of Newton's method as being a residual correction method. So you have an approximate solution to this root, which means you put in the approximation and you don't get zero on the right-hand side. That's the residual. And then you solve a linear system that gives you a correction to the approximate solution that you had, which in general will make the residual smaller than it was before. Now, if you remember Newton's method from the scalar case way back from first year calculus, you know that Newton's method is not robust. You need a reasonable starting guess to the solution of the nonlinear problem to be able to for Newton's method to converge. So if you're talking about time stepping, this isn't really an issue because if you're taking a relatively small time step, the solution that you're computing is not that different from the solution at the previous time step, and so you have a good initial guess to the problem. If you're looking at steady state problems, there is sometimes difficulty finding um, a good approximation of the root that you can start from. And in those cases, you can do something called continuation, where you don't just look at one problem, you look at a sequence of problems, starting from the problem you want to solve, and then moving, no, starting from an easy problem and working towards the problem that you want to solve with a parameter that goes 0 to 1 between the two problems. So you start with the solution of the, I forget what side I'm on now. You would start with the solution of the easy problem, you solve it, right? And then you try and use that to, oh, now I've forgotten, to as an initial guess to the problem you want to solve. Well, maybe that doesn't work, in which case you look at half of the parameter, right? And then you try and use the easy problem to get halfway, and then go on. And then you can imagine you can make this into an adaptive algorithm if you need to. So very difficult nonlinear problems. This is a way that you can approach them. And of course, nonlinear problems can have more than one solution or no solutions. And so you have to know something about the problem that you're trying to solve to know, does it have a unique solution? And then you just have to get close enough to it with an initial guess to find it. Or, could there be multiple solutions, in which case you may have to search around a little bit to find the one that you want. Okay, so I'm going to turn you loose to the more basic notes on Newton's method and vector Newton's method. So if you've never seen that before, I would suggest you pause this video and look through those. And then coming up, I'm going to take you through a discussion of what Newton's method will look like for a nonlinear differential equation approximated with the finite element method. And, I could say you could probably work out how that goes. But the, it's not hard. It's just there's a lot of details to think about and get right. And so hopefully the notes I'll show you next will help you with that. And after that, there is some of my own research you can look at. I've attached a paper to the Notes 18 entry on the web page. This is a paper I wrote a few years ago with a bigger group where we were looking at numerical methods for a class of phase field problems. Don't worry about the more sort of complicated phase field problems that this numerical framework also works on. Look at the simplest one, which is the Allen-Kahn equation. It's a reaction diffusion equation. So the reaction term is nonlinear. And it's a stiff problem, so you have to use implicit time stepping. These are sort of microstructure problems in material science. And so when you're looking at, a tiny piece of the microstructure in a bigger piece of the material, it is reasonable to look at the problem in a periodic cell. Okay, so it's an idealized setting, but it tells you what's happening in the material away from boundary effects. And once you're in a periodic cell, then it opens up the door to spectral methods. So Fourier spectral approximation is what's used in that work. And then you're looking at tying together just some things that we've seen so far in the course. You have to use implicit time stepping. And so then you have a nonlinear system to solve based on a spectral approximation, which you want to find with iterations based on Newton's method, but every matrix from the Newton iteration salts is a full matrix in this spectral method context. If you read through the previous notes, you see how that goes. And so you definitely don't want to make that full matrix and use it in a direct solve. So then you use conjugate gradient methods. These problems are a gradient flow, which means that the Jacobian matrix will be symmetric, and if the time step is small enough, it's positive definite, so you can use vanilla conjugate gradient methods. And to make things work in a reasonably computationally efficient way, there's a preconditioner that is based on a heuristic, but then there's some analysis in the paper, asymptotic analysis in the paper of how well that is expected to work, which matches up with computational evidence. So there's some interesting things to look at there. I just think that's a nice example. I mean, it's my own work, right? So I guess that's why I picked it. But of the things I've done, I picked that one to show you because it ties together the whole sequence of things that we've talked about in the class. As always, I hope everyone is where they want to be now, because I think we're going to be there for a while now. I'm getting a little sick being at home, but at least I have food in the fridge. I got some company. So I hope you're in a similar situation wherever you are, and I will have an announcement I'll put out on the educational management page. You know, these email messages I send out. I'm going to send out something today when this lecture is posted, to tell you this lecture is posted, but also some policy changes that I had on the final grades. Policy changes that will have no effect if you just continue with the course as is, but gives you some options if you have other priorities right now, more of a priority than doing some end of term Math 521 stuff. So it'll give you an option if you're in that situation. Anyway, hope you're all well. Coming up is what the finite element method looks like for a simple nonlinear boundary value problem. Okay, let's have a look and see what this looks like for a simple differential equation problem. This is the simplest nonlinear differential equation that I've been able to come up with. We're back to the 1D periodic setting, but now instead of a linear term, we're going to have this cubic nonlinearity in the problem. And this is a convex problem. It has a unique solution. I should say it has a unique solution. Okay, maybe you have to add an extra term. Anyway, convex problem, and I believe it has a solution that's smooth for every smooth right-hand side. Okay, let's think about how we start off with a finite element approximation. We look at the weak formulation. So we would multiply by a test function. I'm going to be looking for a weak formulation solutions in H1 in this periodic setting. So I'm going to multiply this equation by any arbitrary function in H1 periodic. And then I'm going to integrate by parts, and I'll get the usual Dirichlet term here. And then this term I just have to leave as what it is. These inner products are L2 inner products, so they're this is the integral from 0 to 1 of u prime times v prime. Similarly, we've got all of that stuff. Okay. Step 1, we have a weak formulation. Now let's look at a finite element approximation based on that weak formulation. We'll look for a conforming approximation. So we're going to take an n-dimensional subspace in the function space. We'll have coordinates if we decide on a basis for that space. This is all stuff we've done before right at the beginning of term with some generality about what kind of spaces we had and the basis functions for them. And then we're going to look for a solution in that subspace, and we can write it out as coefficients times a basis. Remember, these coefficients don't always have to be function values of the approximating function, but for many of the cases that we looked at, they are. And we want to solve for the solution vector u. And how do we get it? So what we do is we test this with the approximation for the solution, not with all v, but with all v in the subspace, which means because this is a linear in v, not in u, but it's linear in v, this will be true for all v in the subspace if it's true for all basis vectors. And so if we look at this relationship with this approximation for n basis vectors, then we have n nonlinear equations for the vector u. Let's look at what those equations look like. So first of all, this term looks exactly the same way it did before. I have, pardon me, I have a matrix times the vector, where the matrix is the usual stiffness matrix. This is the integral of phi I prime times phi j prime. And over here, now I have something new. Here's what the nonlinearity is. I'm going to have to look at this one more carefully, which I'll do on the next page. I've got this whole cubic term tested against a basis function. And then here, I have the usual quadrature problem where I approximate these integrals, which are done on a finite set of subintervals. Okay, let's go on to page 2. This is the term that we're looking at. So every q, every basis function I test this thing against, gives me a quantity, this qj. And if you think about it, it's the same story as we've had before. This is something where we have a small number of subintervals where this thing is going to be non-zero. And let's think of the piecewise linear case in the back of our mind. Here is the basis function I'm considering. And so anything outside of these two subintervals is not going to contribute anything to this quantity. So I just have a sum over two subintervals. And on each subinterval, I can scale to the reference interval. In y, although I see I should have some y's farther down, right? So now I'm going to have the single subinterval. So I'm going to have two pieces to this. So this is one, and the other one I'm not talking about. So on this subinterval, the psi k in this interval corresponding to that one is this elementary basis function that slopes this way, right? And in here, I'm going to have u determined by the value here and the value here. This is piecewise linear things I've got in the back of my head where p is equal to 1. So I have two terms, and I'm going to have this UL here, right? So these L's will depend on the specific J that I'm looking at and the specific subinterval in the computation of QJ. But in this subinterval on this side, then I've got this L in brackets 1, that is this value at J minus 1, times the elementary basis function that slopes this way. And then I'll have the L equals 2 term will be UJ, and it will be multiplying by the elementary shape function that slopes this way, the same as the psi k. Now, for specifically our cubic nonlinearity, then these things would be polynomials of degree k. So if you cube this one and multiply by another one, then these will just be integrals of order 4p. And you could do those analytically, and they would involve powers of these ULs. You could do it that way, but in general, you want to allow for more variety in terms of nonlinear functions. And so typically they would be done by quadrature. So here is where I should have a ym, right? Because these are quadrature points in the reference interval. But I'm just going to approximate this integral with the Gaussian quadrature with the m points. Okay. Well, quadrature of any kind. I'm picking Gaussian quadrature. That's what you would pick in generically because it is the highest order accuracy for the number of points that you have. So the integrand depends on y. Okay, so y, not x, through these terms. But it also depends on the values of the grid values that are active on the subinterval. In this case, with these piecewise linear things, that would just be uj minus 1 and uj, which we had labeled in this generic way. So with all of this, if I go back, you can work out all of the QJs as the sums over subintervals as described below. So you can work out all of this stuff for a iterative approximation to the solution of the nonlinear equations, which won't give you exactly 0, but it'll give you a residual that then you can correct with Newton's method. But if you're going to proceed with Newton's method, then you have to find out the Jacobian of this nonlinear system. And the interesting part is this thing, which looks a little bit complicated, well, this is already linear, right? So if I look at the Jacobian matrix of this nonlinear set of equations, well, this doesn't depend on u, so that doesn't show up in the Jacobian. This thing is already linear, so the Jacobian matrix is going to be the stiffness matrix, and then plus the derivatives of these QJs with ui. Now, if you go back to the example, right, this will also only involve I is equal to j, j minus 1, and j plus 1, because all the other u's don't affect QJ at all. So when you're working out this partial derivative, you're also going to work it out as a sum over subintervals. So if we go back to the subinterval that we were looking at before with this approximation, right, then what we have to do is to take the derivative of this stuff with respect to one of the u's that appear in the expression. So here again, I would have a derivative with uj minus 1 and a derivative with respect to uj. how, and again, this should be ym, right? How that looks back for our original thing, right? So now we're taking the derivative of this stuff with respect to one of the u's that is in this expression. So I'm just going to use the chain rule. I get 3 times that expression squared. And then I'll take the derivative with respect to ul, which is just psi l, right? And of course, this is all evaluated at ym, right? So I'm going to take these shape functions, I'm going to evaluate them at ym. I'll take my current estimate of u in my Newton iterations to compute this quantity. I'll get the Jacobian, and I'll be able to update the solution with Newton's method. Now again, this is a particularly nice problem that we started with. And if you thought of a Newton-like iteration in the continuous space setting, which you can do, that iteration converges with any initial guess because of the convexity of this problem. And once you throw in the Gaussian quadrature, that would be very hard to prove that you have the same behavior in the discrete setting, but I believe you will not have any problem with this particular discretization of that nice problem. Okay, so now you know about vector Newton's method. You can see how it would be implemented in a finite element method. And you notice there's a lot of bookkeeping details that you'd have to look after. But if you thought that this was a nonlinear function of u, right, and someone could work out, this is just a scalar function, right? Someone could work out for you what the partial derivative with respect to u of whatever this expression was. That's all you would need in a code to work out this thing, right? And then otherwise the structure is the same. So you could imagine now a finite element code implementation which allows for nonlinear problems. You would have to give it the nonlinearity and the derivative of the nonlinearity, or perhaps it would work it out with some difference approximation, the derivative, to get an approximate Jacobian. And the finite element code could look after all of these details for you. So certainly if you have a code available that will handle nonlinear problems, this is probably what it's doing inside its in its workings. Okay, that ends the material for this lecture. As I said in my my opening, face-to-face portion of this lecture, there's the paper based on some of my own research with a nonlinear problem, nonlinear time-dependent problem, where there is a implicit time stepping with the Newton solver, and the Newton solver is done, the linear solves in the Newton iterations are done with a conjugate gradient method that's preconditioned. And so if you're looking for, a kind of a story where many of the topics that we've talked about this term are wrapped together, I encourage you to have a look at that. Good luck, and next week we will have a special topic yet to be determined, and I will let you know when notes and other things are posted on my webpage. Good luck, everyone.